Announcements. I expect you've seen this. I hope you have. There's all kinds of past exams for this gathering, posted on Sockeye and available for you as reference to present class material as well as exams. If recently you used exam 1 from summer 12, when I last taught this course in the summer, as a reference, please note that I use past exams as a guide in constructing present exam. So of course I used exam 1 from summer 12 as a guide for the exam I'm presently writing for this Friday's Fun and Games activities. That doesn't mean the material is the same or the questions. I just use it as a guide to remind me about the stuff that I wish to ask about. In so doing, I noticed a couple of goofs on the exam key. I fixed the goofs. So if you have used the key to exam 1 in recent times, I suggest you take a look at the present exam key to make sure you got the right information. And as I suspect you all know, exam 1 travels toward us this Friday. I purposely have exams run in 2 sessions. I do not want you to be under time pressure to deal with this stuff. I want you to have every ample opportunity to show me what you know. And in order to do that, I try to remove any time constraints. So practically speaking, for each and every exam, in total you'll have more than 4 hours for every exam. Plenty of time, provided you know what's going on. If you don't know what's going on, I can give you all week. It won't do you any good. But if you know what's going on, you really have available, I'd say, on the order of twice the amount of time you need. But that depends on you and how well you know and understand the stuff that we shall ask you about. Part 1 of the exam will be the first page. You'll do that this Friday during discussion class. So you'll have the full 75 minutes. We'll even steal an extra few minutes if we can. So be on time. Because if you're not on time, you're going to lose time. Part 2, as the syllabus tells you, it's Friday evening. I'm sorry. This Friday you'll have to delay pizza and beer or postpone it to another evening. 7 p.m. to 10 p.m. in a location which I expect you can all find with ease. CLBC 130. The lecture auditorium where I expect you all sat for Chemistry 2045. This will be the format for exams 1, 2, 3. For the last exam, exam 4, call it the final, which to a certain extent will be comprehensive, and I'll give you a lot more information about the final at the end of the term. You'll have 3 hours for each part. And for exam 4, the first part will be 2 pages rather than 1 page, as will the second part. All second parts will be 2 pages. All first parts will be 1 page, except for the last exam. 2 pages and 2 pages. Okay. Acid-base chemistry. Indicators. You were introduced to indicators by way of your work in Chemistry 2046-2045 laboratory, by way of your work in 2046 laboratory assignment number 1, and by way of what's already taken place in discussion class. Indicators are organic dyes, which have very low energy valence electron structures. By low energy, I mean that the valence electron structure of an indicator is excitable by the rather low energy radiation that comes to us from so-called white light. stuff we have with us in this room. Consequently, as a function of pH, we can use indicators because of the colors they show as pH varies to give us a handle on system pH. In laboratory, you will use indicators essentially exclusively to get handles on unknown samples as well as known samples whose pHs you need to assess. If you've read the information in assignment 2, laboratory, regarding unknown analysis, you have recognized that the most important single test you can do on any unknown sample is solution pH. Because we promise that in making an unknown sample, we will not mix pH incompatible materials. We will not mix materials like sodium hydrogen sulfate and sodium hydroxide. This hydrogen sulfate ion and hydroxide ion kill each other to a large extent. So based on the mole ratio of hydrogen sulfate ion to hydroxide ion, I can make any pH I want all the way from 1 to 14. So if I play games like that, solution pH wouldn't mean anything. But to make pH investigation a valuable assessment, the most important single assessment, we promise you, as is stated in the laboratory manual, that in preparing unknown samples, we do not combine pH incompatible materials, which means pH investigation will provide a direct reflection of the components of the sample. Now, that stuff again will be done by indicator analysis. It's quick, fast, reliable indicator analysis. So with that, before we get into these somewhat more detailed indicator considerations, and given that you've been introduced to the fundamentals of indicator behavior, again, organic dyes which show color changes as a function of pH over a particular pH range. Did you realize that if you have the boundary conditions pH for an indicator, the pH values over which the indicator changes color, that you have an immediate handle on the strength of the indicator as a Bronsted acid? You recognize that? Because when the indicator is 50% ionized, you have an equal mole ratio mix of the acid form of the indicator and the conjugate base form of the indicator. And when these forms of the indicator are present in a solution at equal molarity, how does Ka for the indicator compare to the hydronium ion concentration for the solution? They're equal. That's pretty handy information. We'll do more on that in a moment. Now then, arguably, the most commonly used indicator in laboratory when you're dealing with chemistry and water solution is bromethymol blue. I got some here. Bromethymol blue shows this colorimetric behavior. But bromethymol blue shows this colorimetric behavior. I'll put it up here. HBTB. Over a pH range of 6.0 to 8.0. That's really about 7.6, 7.7 at the end. But this is good enough for our purposes. Because with indicator analysis, you can't get better than one significant figure approximation. So if you're using bromethymol blue indicator, and you treat a colorless solution with this indicator, and observe a yellow color, you know that the pH is 6.0 or some value lower than 6.0. What do you think is the better bet? 6.0 or the lower value? Lower value. My golly, this is one data point. There's a multitude of data points lower than 6.0. Same for 8.0. I mean, same for color of blue. The pH is 8.0 or higher, which means the pH is entirely likely to be higher than 8.0, but it could be 8.0. But if with bromethymol blue indicator, you see a distinct yellow-green color, then you have information to support the conclusion that the pH is on the order of what? 6.5. If your eyeballs tell you that this solution colorimetrically is equal in yellow color as it is in green color, hey, it's a judgment call. But a whole lot of what you have to do in the laboratory is to make judgments. So one additional reason why I like you to do indicator analysis to get a handle on pH is you have to make sharp and clear decisions, judgments. Blue-green, pH on the order of 7.5 if it's a distinct blue-green. But if your eyeballs tell you this solution is more green than blue, then the pH will be closer to 7.0 than it will be to 7.5. And if it's distinctly more blue than green, the pH will be closer to 8.0 than it will be 7.5. Be in here someplace. You got to make a decision. Okay? Now, I've got some mysterious colorless solutions here. Cylinder A and flask A. Bromethymol blue. I'm going to put in a good slug of indicator so that we can get reasonably intense colors. Ooh, my. Let's do the same with cylinder B and flask B. And needless to say, the same treatment we apply to cylinder C and flask C. Now, in each cylinder, I have 200 milliliters of solution. I measured them before I set up this demonstration. In each flask, I have 200 milliliters of solution. So for the mixtures we're going to make, in each case, we'll be combining 200 milliliters of a distinctly blue solution with 200 milliliters of a distinctly yellow solution. Maybe you'd like to call it goldenrod. I don't know. It's up to you. Okay? For each case. I ask you, if you can, to predict the color of this mixture. It's the damnedest green I ever saw. All right, let's try again.
Blue.
How about that? One more time.
Right.
Who said red? That's right. Who said green? You seen this before? How about that? Now let's ask the real question. Based on what we did, why was it not possible to predict in any reliable fashion the color of the resultant solution? Why was it not possible?
Because in the yellow solution, you only knew that it was either 6.0 or below. And in the blue solution, you only knew that it was 8.0 or above.
So
you didn't know the actual pH, so you couldn't predict whether the acid was stronger or
Well,
the more acidic.
whether the hydronium ion concentration was higher. That's right. We didn't know anything about moles. But we know after having made the mixture that in cylinder A, Hydronium or hydroxide ion is in higher molarity. Was in higher molarity. Hydronium ion. In cylinder B, hydronium ion or hydroxide ion. But in cylinder C, we recognize that we made a mixture, equal moles, hydronium ion, hydroxide ion, but only in cylinder C. Okay? Good. So, in the main, we want you to recognize from information like this what you can and cannot predict successfully. Now we're going to do another experiment. I need cylinders. Deionized water. That's good enough. Need another cylinder. Now here we got deionized water. Here we got some stuff with which you are fairly familiar. What is it? 1 molar acetic acid solution. I want to collect a volume that's about the same as what we have of deionized water in the first cylinder. Not too bad. I'll put just a little bit more water in this one. How we compare it? Pretty good. Okay? Now then, for this investigation, we're going to use this indicator. Do you remember how this indicator behaves? Shorthand reference for methyl orange. You use this in assignment 1 in the laboratory. Remember the color change range for methyl orange, roughly? It's about 3 to 5. You remember the color changes it shows. Here's methyl orange. As hydronium ion concentration goes up and pH goes down, from the pH range of 3 to 5, if we go from 5 to the lower pH of 3, hydronium ion concentration go up. Methyl orange shows us essentially a color change from yellow to red. Here is the deionized water. Good slug. Well, not yellow. Stop. Awfully orange for deionized water. Let's try this one again. Should be more yellowish than this, but still distinctly different from the other cylinder. Okay. Well, let's call this one goldenrod. And call this one lipstick red. All right? Remember what we got. 1 molar acetic acid treated with HMO, deionized water from the system in Lee Hall, treated with This is not the same system that's in our lab. We have our own deionized deionizing system in the teaching lab because we can't afford for that system to shut down. So there might be something wrong with the system in-house. Shouldn't be more yellow than that. But in any case, we'll take it as deionized water. Same volume as the acetic acid solution. The question is, I'm now going to put these solutions together. Can you predict the outcome colorimetrically? Let's call it red to yellow-orange, all right? So we could get orange, red-orange. There's possibilities. Can you predict the outcome? Colorimetric outcome.
Red.
I heard a vote for red. Anybody else want to vote for red? You voted for red. You voted for red. Who else voted for red? Okay. All right, I'm going to pick on you. Why do you pick red?
Because when you add them together, the hydrogen concentration is going to increase. And since the
What?
increase,
Which of these has the higher hydronium ion concentration?
the red one.
Yeah. Why would you argue that on mixing the hydronium ion concentration is going to increase?
Because you're going to add the hydronium from the deionized water to the acetic acid.
Remember, you said the concentration is going to increase. Is that possible? That's a something for nothing proposition.
Yeah, the volume's going to increase as well.
Volume will increase. Moles of hydronium ion will increase. The concentration is not going to increase. Would you like to adjust your prediction? I'm not trying to talk you into it. I'm asking.
No, I think I would.
You want to change your prediction?
Yeah.
What do you want to change it to?
Orange.
Orange. Okay, we got a change in prediction. Now, some of you have seen this before, so I'm not going to pick on you. All right? You voted red. Yeah? Are you staying with red?
Yeah.
Why?
Because 1 mole of acetic acid, or 1 molar of acetic acid is like 2.3-ish. And since that's not perfectly yellow, it'll probably just end up going to red. Because the red overpowers the orange.
What if I say the orange overpowers the red?
Probably not. 'Cause
Probably not.
it's not-
Now, I want you to understand. You can, if you think about this correctly, flatly predict the colorimetric outcome. Correctly predict. I want to know how and why. How many vote that the resultant solution color will be intermediate between? How many vote that the resultant solution color will be essentially the same as the deionized water? How many vote that the resultant solution color will in fact remain this color? How many didn't vote? 2 million off exam 1. Stayed red, didn't it? See, your prediction was right, but your explanation wasn't. Now, I'll give you another chance to explain. I'm going to give you a hint.
Okay.
Remember, we put together equal volumes of liquids.
Right.
This was 1 molar acetic acid, and the other was deionized water. What in fact did we do by combining 200 milliliters roughly of deionized water with 200 milliliters of 1 molar acetic acid? I turned 1 molar acetic acid into,
0.5.
how about that? Does that change the hydronium ion concentration much in acetic acid? We've done a number of acetic acid hydronium ion concentration analysis already. It doesn't change the pH much at all, does it? That's why the color changed the same. Because the other property of indicators, which you already heard about, is that in order to see a distinct color change, you usually need to change the pH at least about 3/10, 4/10 of a pH unit. We didn't make any change like that at all. If you want to answer this with calculation, you calculate the hydronium ion molarity for 1 molar acetic acid and calculate the hydronium ion molarity for half molar acetic acid and see how they compare. Going to be pretty daggone close. That's why the color stays essentially distinct red. All right, now then, question 1835. I got the critical data on the board. The indicator in question is one of my homemade hypothetical indicators, HGX, Gator xanthus. Color change range, 0.9 or a lower pH, distinctly yellow. 2.5 or a higher pH, distinctly blue. Tell me, at what pH for this indicator do we see a distinct green? Tell me and I'll write it down. Distinct yellow-green. Distinct blue-green. You see that to answer each consideration, all we did was to take the range, the boundary pHs, and divide by 2. Add them together, divide by 2. If I have 2 solutions which bear these respective hydronium ion concentrations. Equal volumes. Let's say 100 milliliters of each. I mix these 2 solutions. Can you, in a straightforward fashion, get the hydronium ion concentration for the solution which results by dealing with concentrations? Those are the concentrations. I'm going to mix 100 milliliters of this solution, 100 milliliters of this solution, and the question is, what is the concentration for hydronium ion? That's halfway between. What is the hydronium ion concentration that's halfway between these boundary values? Anybody got an idea? Statement.
0.005.
What is that?
0.005 molar.
Did I remind you earlier why logarithms were invented? They weren't invented to make your life miserable in math class. Logarithms are a really powerful mathematical tool because they reduce exponential equations to linear equations. Equations which can be solved by addition or subtraction. Pretty good. You can't do that with exponential equations, and concentrations are exponential. But pHs are logs. Hydronium ion concentration that's halfway between these values is the go ahead.
0.0055.
No. That's a poorer answer than the first one we got. That's all right. You're participating. Tell me, what did you do to get this answer?
I converted the hydronium ion concentrations to moles, and then I added them together, and then I divided by the total.
Won't work. The hydronium ion concentration that's halfway between these boundary values is the concentration, which differs from the boundary values by the same factor. That's the hydronium ion concentration that's halfway between. So the hydronium ion concentration that's halfway between these values has, of course, got to be smaller than this value, but greater than this value. What's the simple way to get this halfway hydronium ion concentration? The simple way.
Average them.
Do what? Average them won't get you the answer. The simple way to get the halfway hydronium ion concentration. Here's the simple way. What's pH for this solution? 2. What is it? 2. It is not? 2.0. It is not?
2.00.
That's correct. Don't forget significant figures. There's the halfway pH. And the antilog of that value is 3.2 times 10 to the minus 3. Because 3.2 times 10 to the minus 3 is 3.2 times bigger than this value. And this value is 3.2 times bigger than 3.2 times 10 to the minus 3. How about that? Be careful. Halfway hydronium ion concentration. Difficult to get because concentrations are exponential. All right, that's an arithmetic lesson. Now let's get back to chemistry. Tell me, for our indicator HGX, what's Ka value? At this pH, HGX is 50% ionized. So the hydronium ion concentration at this pH is Ka for HGX. What's hydronium ion concentration at this pH?
2.0 times 10 minus 2.
Try again.
2.0 times 10.
Try again. Try again. How many significant figures is this value? How many? 1. This is a log. This is a characteristic. This is a mantissa. And characteristics are decimal point locators. They have no bearing on measurmental significance. Only the digital entries in the mantissa count. That's logs. You have to know this stuff. That's 1 significant figure. So I ask again, what's Ka for HGX?
2 times 10.
What is it?
2 times 10 to the negative second.
And the statement of this question in the notes tells you that HGX and this unknown acid HQ are the same strength. So what's KaHQ? This is the only handle we have on quantitative acid strength. Ka. So if HGX and HQ have the same strength, what's Ka for HQ?
Same.
Same.
Wait, how did you do that number?
What is that?
That number. I don't understand how you got that number.
This number? That's the hydronium ion concentration at this pH. Remember this? There's the chemical version of the equilibrium constant for HGX behaving as an acid. Okay? And that by definition is KAHGX. This corresponds to HGX reacting with water to make hydronium ion
I
and...
don't understand how you got that for 1.7.
Well, wait. You understand this part?
Yeah.
Goody. Now then, at this pH, to what extent is HGX ionized? Why do you see the green color? Did you play with colors when you were a kid? Yellow, blue. If you want to make a distinct green and you start off with yellow and blue, what do you do? In what ratio? If you want a distinct green, right? And for indicator HGX, what is yellow? HGX or GX minus? What is blue? HGX or GX minus?
Yellow is HGX.
Mm-hmm. And blue is? That's right. And so, at this pH, where HGX is 50% ionized, how do these molarities compare? Why do I see the green color? So at this pH, the hydronium ion concentration is equal to Ka. So the hydronium ion concentration at this value is 2 times 10 to the minus 2. That's how I got that number. Now, given with this information before us, let's quickly consider 1836. Because the notes tell you that this unknown acid HC is twice as strong as HGX or HQ. So what's Ka for HC? What is it? What's Ka for HC? If it's twice as strong as HGX? 4 times 10 to the minus 2. We did that one now because we just got Ka for HGX as well as HQ. Okay? Now then, to continue with question 1835.
How do we know that HC is 2 times stronger? Are you just giving...
I'm just telling you that. Okay? That's a given. Okay? Back to 1835. The second part of 1835 tells you that we have an Hg solution which is treated with this indicator HGX, and for this solution we see a distinct yellow-green color. So we'll take the pH to be 1.3. At pH 1.3, what's that hydronium ion concentration? When we talked about pH a short while back, which you did in discussion class, did you see the information in the notes on dealing with pH arithmetic? I'm just curious. If you learn logarithms for numbers between 1 and 10, you can do this pH arithmetic really fast. By definition, what's the log of 1? 0. That's where it all starts. What's the log of 2? The 4 sig figs, if I take 2.0000, it's 0.3010. What's the log of 3? 0.4771, the 4 sig figs. What's the log of 4? Do I need to memorize that one? No, because that's twice the log of 2. What's the log of 5? 0.6990. What's the log of 6? Do I need to memorize that one? No, because that's the log of 2 added to the log of 3. What's the log of 7? 0.8451. What's What's log of 8? Do I need to memorize that one? No, that's a log of 2 times multiplied times 3. What's a log of 9? Do I need to memorize that one? No, because that's a log of 3 doubled. What's a log of 10? 1.0000. Hey, it's not hard to do. And if you do this for yourself, you can do this pH arithmetic just as fast as I do it. Using the best calculator you got. This one. See, in my day, we didn't have calculators. We had slide rules. And I never found a slide rule with which I could do logarithmic arithmetic. So when my instructor told me to learn the pH values, which I just cited to you, I gave you the log of 5 incorrectly. It's 0.6991, not 0.6990. Big deal. Okay. Hey, in short order fashion, you can do this pH arithmetic quickly. And the best part of it is you'll understand it a lot better. That's why when I look, for example, at this pH, I can see at a glance that the hydronium ion concentration is 5 times 10 to the minus 2. You can check it. But if you do this stuff, it'll make so much more sense to you. And it'll be so much easier to deal with. On we go. We want to get m sub I for this Hg solution. All we know about it is that it shows a distinct Yg color for which the pH is 1.3 and the hydronium ion concentration is 5 times 10 to the minus 2. So we know this. There's the chemical version of Ka for HQ. The hydronium ion concentration is 5 times 10 to the minus 2. What's Q minus? Molarity. 5 times 10 to the minus 2. There's only one solute in here. It's HQ. Ka is 2 times 10 to the minus 2. What's the equilibrium molarity of HQ in terms of what we know? The equilibrium molarity of HQ in terms of what we know. Algebraically, what's the equilibrium molarity of HQ? This look familiar? For this solution, what is this? It's m sub I minus what? 5 times 10 to the minus 2. There's the derived species, Q minus. Remember, there's none but material balance consideration applied to this particular solution. So I got this, I got this, I got this, and I got this. How many unknowns I got? We solve it. And we get something. That. Because we can't go past 1 sig fig. You can do the arithmetic. Okay? We proceed. And now we go to solutions which I'm sure you've all heard about. Blood, sweat, tears. Each example is a very important human buffer systems. Urine also. You upset the pH for these systems, we are not well off chemically. What's the main function of a buffer?
Maintains pH.
Let's define it as a singular buffer or buffer solution. A solution. Oops. With primary function of pH maintenance, pH preservation if you prefer. How's a buffer usually prepared? Usually. By mixing. In high concentration. A weak Bl acid with its conjugate base. Because if we're going to make a stable acid-base solution, we have to use compatible acid-base species, not acid-base species which kill each other effectively. For example, a solution which is 1 molar in both acetic acid and acetate ion. Or a solution which is both 1 molar in ammonium ion and ammonia. I mean, we could put down a bazillion examples. That's not necessary. Question. If I make the acetic acid acetate ion buffer, is this acidic, basic, or neutral? If I make this buffer, acidic, basic, or neutral? How do I find out?
I compare the KAs and the KBs.
Ka of what and Kb of what?
Ka of H4n plus and Kb of H3n.
What is Ka for H4n plus? Got your acid base table?
5.6 times 10 to the minus 10.
What's Kb for acetate ion? I mean, pardon me, ammonia. Ammonia, since we focused on the ammonium ion buffer. Interestingly enough, Kb for ammonia is numerically equal to Ka for acetic acid. The two significant figures. But that's serendipity. There's no chemical foundation for this equivalence. So, does this information tell us why the ammonium ion ammonia buffer's got to be a basic solution? Do we see? Isn't this Kb number a heck of a lot bigger than the Ka number? That means ammonia does a whole lot better job reacting with water to create hydroxide ion than ammonium ion does in reacting with water to create hydronium ion. Well, if we apply the same consideration to the acetic acid acetate ion buffer, Ka 1.8 times 10 to the minus 5. Kb 5.6 times 10 to the minus 10. So this buffer is acidic. All right. Now then, we know that the primary function of a buffer is to preserve pH. Well, how does this happen? pH measures hydronium ion molarity or hydroxide ion molarity. That's what it measures. So if a buffer is operating correctly, if I add a source of H plus to a solution or a source of hydroxide ion to a solution, somehow, some way, what's going to happen to the H plus added or the hydroxide ion added if the buffer's doing its job? What's going to happen to the H plus added or the hydroxide ion added? What's going to happen to this buffer solution if I put in HCl? That's a marvelous source of H plus. What's going to happen to this buffer if I put in hydroxide ion? That's a marvelous source, sodium hydroxide, which is a marvelous source of hydroxide ion. Or vice versa. Consider putting the hydroxide ion in here, HCl in here. Doesn't make any difference. What's going to happen? You know how to play the game. You start with what consideration? What is it? What is it?
PSI.
PSI! So you know what you're dealing with. Then you answer the question. If I take this buffer or that buffer, I don't care which one, and I add HCl gas in this buffer solution, what's the HCl gas going to do? It's going to react with water and make hydronium ion? Or instead, will the HCl react with what? With what? In this solution, what's the HCl added react with? Acetate ion. That's the strongest base present in high concentration. Okay? What's the extent of this reaction? How large? To what extent does HCl react with water? 100%. This is a stronger base than water? Well then, if HCl can react with water 100%, and I put it together with a stronger base, it's going to react 100%, that's for sure. If I take this buffer and dump in sodium hydroxide, what's going to happen? What's hydroxide ion added going to react with? Is hydroxide ion just going to float merrily into solution and in so doing up the hydroxide ion molarity? Or is there something in here that'll kill the hydroxide ion when I added it? Like this. And create ammonia and water, large extent. Right. All follows from the acid-base reaction considerations we've done already. PSI, what's going to happen when I put this in? This, in this case, shows us how a buffer behaves. All right? Now then, let's take a look at hypothet for hypothetical buffer HXX minus. Okay? If I wish to get at a very often considered property for this solution, what do you think this property is? From an acid-base standpoint, what solution property am I very often interested in?
pH.
pH! Yeah, I want to get pH. I need to recognize, for starters, that in this solution, what is the principal acid-base equilibrium which exists? Write it on your paper right now. This stuff is all in the notes, but it's important. That's why I'm plowing through it right here and now. In this solution was the principal Bronsted-Lowry acid-base equilibrium reaction. Will it not involve the strongest acid at high concentration in this solution? And that acid is? Will it not involve the strongest base at high concentration in this solution? And that base is? How about that? There it is. The principal Bronsted-Lowry acid-base equilibrium reaction in this solution. Does this reaction lead to any chemistry change for the system? Any composition change? Does this reaction give us a handle on pH? No, no, and no. So even though this is in fact the primary Bronsted-Lowry acid-base equilibrium in this reaction, it doesn't get us any place from a chemistry standpoint. So if I want solution pH, for example, I got to look at a different equilibrium reaction. Different than this one. And it better be an equilibrium reaction which contains what or what?
Hydronium or hydroxide.
Yeah, better have hydronium ion or hydroxide ion in it if I'm going to get a handle on pH. So I can write, consider HX plus H2O. For speed, I'm leaving out subscript AQ and L and all that stuff. You can put that in. Or X minus plus water. Double arrows. HX plus hydroxide ion. It matters not which of these equilibrium reactions you consider, because they both involve principal species and they both serve the purpose of giving us a handle on pH. Just like here. I can look at acetic acid plus water equilibrium or acetate ion plus water equilibrium. Ammonium ion plus water equilibrium or ammonia plus water equilibrium. I've seen textbooks make the claim that this is a basic buffer, so I have to use the ammonia reaction. That's wrong. Textbooks make the claim this is an acidic buffer, so I have to use the acetic acid reaction. That's wrong. They're not paying attention to PSI when they make statements like that. So, I'm going to use this one. I can use the other one. But I'm going to use this one because it's got hydronium ion in it, and pH is more directly a measure of hydronium ion molarity than hydroxide ion molarity. Each one can be used. It makes no difference. So I'll write KaHX equals hydronium ion molarity times X minus molarity over HX molarity, all equilibrium values, okay? And then watch out, because I'm going to do some logarithmic arithmetic. Log Ka equals log of the hydronium ion molarity plus log of X minus molarity. Remember these logs? They turn these things into linear equations. You crack them by addition or subtraction. Minus the log of this stuff. There it is. The result of the logarithmic arithmetic. Now let's do some simple rearrangement with this statement, this equation. Log hydronium ion. I'm going to take the log hydronium ion, I'm going to put it on this side of the term. And I'm going to put the pKa on the other side. log Ka, pardon me. Now I'm going to put these two terms, log x minus log hx together. Now, from an arithmetic standpoint, be sure that you see that this is not this is not this. Now, after having done this rearrangement, what's this? How about that? So now we got an equation for pH. Has a name called a Henderson-Hasselbalch equation. Any of you ever do any chemistry in a physiological chemistry laboratory or something like that? Have you heard about this Henderson-Hasselbalch stuff? Doesn't matter, you won't hear about it from me again. Those names don't mean a damn thing. If I develop something that's important, it's the something that I developed that's important, not me. On we go. We now got a handle on how to get pH for a buffer solution. So let's try question 1838. Milliliters of 0.80 molar ammonia solution. 100 milliliters. 1.0 molar ammonium chloride solution. To this, add 0.020 moles of HCl gas. And get the hydronium ion concentration. And of course, then if we want pH, we can calculate pH. No big deal. What do we need to do? What do we need to do? We're on the board, practically. This solution right here. What's PSI for that solution? And water, of course. This solution? Ammonia, water. And we want to calculate a concentration value. So how do we have to consider these inventories? From what standpoint? Quantitative. Okay. How many moles of ammonia do I have? How many moles ammonia? Keep going.
0.
How many moles of ammonium ion?
.01.
Now, we've argued that the principal function of a buffer is to serve the purpose of preserving pH. Which means, if I compute the pH of this solution now, and then consider treatment with the HCl, and recompute pH, will I see much pH change? No. Now, what total volume do we have here? 200 milliliters, right? So I'm going to do this to give you a better idea of how, from a quantitative standpoint, buffers behave. Let's add 0.020 moles of HCl, because that's how much we're going to put in this buffer. To 0.20 liters of DIW, deionized water. Do we see much of a pH change here? Right here. On making this mix, will we observe much of a pH change? Does water have a high concentration of a weak Bronsted acid? It does. What's the acid? It's called water. Does water have a high concentration of weak Bronsted base? Yeah, what's the base? It's called water. So is water itself a buffer? Tell me, here's deionized water. What's the pH? Two sig fig, 7.00. Hydronium ion concentration? (1.0 times 10 to the minus 7 to 2 sig figs. Now let's put the HCl in there. 0.020 moles of HCl is bubbled into 0.20 liters of deionized water. How does the system inventory after I make this mix? Will I get a reaction on making this mix? What reaction will I get? Isn't this just like making hydrochloric acid solution? HCl, water, hydronium ion, chloride ion. To what extent does this reaction proceed? 100%. How many moles of hydronium ion am I going to make? 0.020. All the HCl I add is going to convert to hydronium ion. And this 0.020 moles hydronium ion will be contained in what volume? 0.20 liters. What's hydronium ion concentration? Watch out, this is tough. 0.020 divided by 0.20. What's the hydronium ion concentration?
410.
0.10. What's the pH? One. 1.00. pH changed by 6 units. And each change is a hydronium ion molarity of power of 10. I changed the hydronium ion concentration from 1.0 times 10 to minus 7 to 1.0 times 10 to minus 1. I changed the hydronium ion concentration by 1 million. Is that a pretty good change? How about that? So is our water itself a buffer? Hell no. Now what's going to happen when I make this system? You do the arithmetic and we'll pick it up from this point tomorrow.